Hello and welcome to this mystical chemistry video where I will be going through the carboxylic acids and esters practice test. Straight into question 1a, we are asked to add curly arrows to our mechanism. In order to be able to do this, we have to use our understanding of what curly arrows mean. A curly arrow is the movement of a pair of electrons. They must always start where there is a pair of electrons, such as a lone pair or a bond, and end where they are going, such as where a bond will form or on an atom that is going to become ionized. Looking at our example here, we have some curly arrows written on already. So you can see that the OH- is attacking the delta positive carbon because the arrow is moving from the lone pair on the oxygen to where a bond will form between the carbon and that oxygen. Now, to work out what else is happening, we need to be able to compare our current substance, so the substance prior to step 1 occurring, and the first intermediary, so the molecule as it stands after the first step occurring. The major difference, other than the fact that we've formed the bond between the oxygen and the carbon, shown by the arrow that's already there, is the fact that we've gone from a C double bond O to a C single bond O minus. The minus sign tells you the direction of the travel of charge. If it's gone from being neutral to negative, electrons must have moved towards it. Therefore, the breaking of the double bond to form the single bond was heterolytic, with the electrons moving towards the oxygen. The second curly arrow represents the changes that are occurring in step 2. You can see one of the steps that's already occurring, which I've highlighted there. You can see the oxygen with the minus sign on it is reforming the double bond, as shown with the curly arrow that they've written. The other change is the fact that we are losing a bond between the carbon and the oxygen at the bottom there, which I've just highlighted there. So electrons must be moving from this bond away from that bond to break it. There's two choices in terms of where the electrons can go. They can either go onto the carbon or they can go onto the oxygen. Remember that if an electron moves towards something, it's going to become more negative. If electrons were to move from the bond onto the carbon, then the carbon would be becoming negative. If we look at the product of step 2, there is no negative charge on the carbon, so we know that the electrons must have moved away from it. So our arrow would look like this. It's also worth noting that that bond is breaking in order to keep the right number of electrons on the carbon. If electrons were to move from that bond onto the carbon, we'd end up with 2 extra electrons, no idea where they'd go, wouldn't make any sense. The third step is explaining what's happening in step 3. So if you look at the arrow that's already there, you can see that the O- is attacking a hydrogen, and you can then see in the final product that that hydrogen has gone. So that bond between the oxygen and the hydrogen must be being broken, so this bond here must be being broken, and the question of which direction the electrons are going to go in is answered by the fact that the O- sign is present, the minus sign is present on the product at the very end. That means the electrons must be moving away from the bond and onto the oxygen. So we will see that. Again, much like in the previous example, the previous step, the breaking of the bond is in order to keep the right number of electrons around the atom. If you were to have the electrons moving onto the hydrogen, there'd be too many electrons in the hydrogen, wouldn't really make any sense. So there are arrows. If I get rid of my highlights, so you can see what you should have drawn. Question B asks you to state the type of reaction. Note that it isn't after the mechanism name. So mechanism names typically tell you the method of attack, such as nucleophilic or electrophilic, and whether it is an addition reaction or a substitution reaction, etc. This question is not doing that, however. It is just asking for the type. In this reaction, a small molecule is being used to break the ester apart. It is therefore a hydrolysis reaction. Question C wants to know the role of the CH3O- ion. The first thing to do, of course, is to start by identifying the ion and seeing what it's doing. So our ion is this here. And you can see that it is attacking the hydrogen. Another way of writing that, of course, would be to say that it is accepting the hydrogen from the carboxylic acid. Specifically, it's accepting the hydrogen without taking the electrons. It is therefore acting as a base. Question D wants you to state a use for the products. This is an example of a saponification reaction. It is used to make soap. The only answer that you can give is soap. Okay, so question 2 is about the reaction between a triester and OH-. When this reaction takes place, the ester link is hydrolyzed, leaving you with a trialcohol and 3 carboxylic acids. It is easier to understand if you draw it out fully. Here on the right, I've drawn out a small section of the molecule as a display formula. You can see on the left where I've highlighted a section, it's that part of the molecule. When you react it with an OH-, you break the bond here and add in an OH. You are therefore left with an alcohol and a carboxylate ion. Now, of course, this is only one part of the triester, so you actually end up with a trialcohol and 3 carboxylate salts. The 3 carboxylate salts are already written for you in the equation, so in order to complete the equation, we need to draw out the trialcohol. The most logical way that I can think of to draw it is like this. The other parts of question 2a, the first one is the type of compound that is drawn out already. So it's saying, what is this? Well, I've already used the term quite a few times. It is a carboxylate salt, and the whole thing is used, just as it was in the previous question, is used as soap. Question B is a calculation question where it wants you to work out the number of carbons in the R groups. In order to do this, we need to work out the MR of the R group. Now, we're told the MR of the whole compound, of the whole molecule, and if we can work out the MR of this section, you can subtract one from the other to work out the MR of the 3 R groups. Let's start by working out the MR of the highlighted section. In that section, there are 6 carbons, 6 oxygens, and 5 hydrogens. That adds up to an MR of 173. Now that we know the MR of the highlighted section, we can subtract that from the total MR to work out the MR of the 3 R groups. And then divide that by 3 to give you the value for each R group. Now we know the MR of CH3, CH2N. We can subtract the MR of CH3 from that to get the MR of CH2N. Then divide by the MR of CH2 to get the value for N. And we have found the value of N is 10. Question C is a back titration question. In this experiment, you have a starting amount of KOH, which is in excess. That KOH is reacted with the triester, but some of the KOH is left over afterwards. If you can work out how much of the KOH you started with and how much you were left with after it reacted with the triester, then you can work out how much was used up in the reaction. Working out the amount of KOH you started with is simple, chemically speaking. Working out how much you have left over after the reaction with the triester is a little bit more complicated. In fact, the whole purpose of the titration with the acid afterwards is to determine how much KOH is left over after its reaction with the triester. So, start by working out the initial moles of KOH. Moles equals mass over MR, so the initial moles of KOH is... Take a moment to note that I am being very neat with the way I lay these out. Okay, I'm saying exactly what it is that everything is, showing the equation, writing the answer. Next, work out the moles of KOH left over after reacting with the triester. In order to do this, you have to work out the moles of HCl. So, moles of HCl equal to concentration times volume, giving you 1.565 times 10 to the minus 3 moles of HCl. As the ratio of HCl to KOH is 1 to 1, you have 1.565 times 10 to the minus 3 moles of KOH. Now that we know the number of starting moles and the number of moles after reacting with the triester, the difference can tell us the number of moles of KOH that we used up in the reaction with the triester. The next step is to use the ratio between the KOH and the triester to work out the moles of triester. In the reaction, we know it's a 3:1 ratio, therefore divide the number of moles of KOH by 3, which gives us 1.980 times 10 to the minus 3 moles of triester. To convert this to a mass, multiply it by its MR, and to work out as a percentage, take the mass of the ester, divide by the mass of the coconut oil, and multiply that by 100. And this gives you your answer of 87.1%. Question D, part 1, is a very practical consideration. If we are trying to react KOH with coconut oil, we need to think about what they'll be dissolved in. KOH would normally be dissolved in water, but water and coconut oil are immiscible, so the reaction won't work. You need to pick a solvent where both reactants can dissolve and therefore mix with each other. The second part is an equally practical problem. Ethanol is flammable, so you don't want to be heating it with a method that will risk contact with an open flame. My recommendation would be to use a heating mantle. Question 3a wants you to identify the chiral carbon. Remember, chiral carbons are ones that have 4 unique groups on them. There is only one carbon that has 4 unique groups on it, and it is this one. Question B wants you to identify the functional groups present in the molecule. The first functional group is an amide, which is this. This functional group is present here. The second functional group is amine, which is this, where those R groups can be a carbon or a hydrogen. There is an amine present here. It's worth noticing that there is what looks like an amine already highlighted. The amide, which contains the nitrogen and the hydrogen, does not count as a second amine. In the same way that if you were to have a functional group of a carboxylic acid, you wouldn't say that an alcohol is present, even though an alcohol, an OH group, is part of the carboxylic acid group. The third functional group is an ester, which is this, and is not present in the molecule. The fourth one is a ketone, which is this, where those R groups have to be carbons. Again, like before, there is a C double bond O present already, but it's part of the amide, so it doesn't get counted as a ketone. So, the functional groups that are present, there's an amide, there's an amine, but there's not an ester and not a ketone. Question C wants you to identify the products from hydrolysis of the molecule. You have to start by identifying the location where the hydrolysis will take place. The only thing that can be hydrolyzed here is the amide. The bond between the carbon and the nitrogen is broken, with water being added where the molecule broke apart. So, broken across there. This results in an OH being added to the carbon and an H being added to the nitrogen. That will produce these molecules. There is one small error here, which is that I have not taken into account the fact that this hydrolysis reaction took place in acidic conditions. The product on the left there is an amine. Amine are bases. Bases can accept protons. There are lots of protons present because this is in acidic conditions, which means that this amine will actually accept a proton, which results in forming the protonated version of the amine. Now, if we're going to be sticklers about it, which we are, this isn't the only amine present. There's actually another amine, the one on the molecule on the right. So technically speaking, you should actually put a hydrogen ion on that one as well. So those are your two products. You can get away with the unprotonated version of the amine on the right, so you can get away with that, but you can't get away with it on the left, so you have to have the product on the left there. Okay, so question D is really just a GCSE biology question. You can answer it with the same level of sophistication as you would have done in GCSE biology, just with the addition of some A-level chemistry terminology. Enzymes have active sites, and only the G enantiomer has the correct stereochemistry to be complementary to it. Question 4a wants you to identify the isomers that would react with warmed acidified dichromate. You are therefore looking for anything that can be oxidized. Remember, primary and secondary alcohols can be oxidized, as can aldehydes. Ketones cannot be, neither can tertiary alcohols. Let's look at each of them individually and decide whether they can react. P is a tertiary alcohol, so it will not react. Q is a primary alcohol, so it will react. R is a secondary alcohol, so it will also react. S, like R, is a secondary alcohol, so it will react. And T is an aldehyde, so it will react. U, however, is a ketone, so it will not react. So the ones that will react are Q, R, S, and T. In terms of the observation, the colour change is due to the change from dichromate to chromium ions. Dichromate is orange, whereas chromium 3+ are green. So you will see a colour change going from orange to green. Question B is a very similar reaction. It just wants to know which substances will react with toluenes. So toluenes is what we use to identify aldehydes. This time it is just aldehydes that will react, so no ketones, no alcohols. The only one that is an aldehyde is T, so the answer is T. The observation that you would see for that is silver mirror. Question C is reacting the substances with ethanoic acid and a sulfuric acid catalyst. This is causing an esterification reaction to occur. The reaction will occur between any alcohol and the ethanoic acid, so it will react with P, Q, R, and S, which are all alcohols. This reaction doesn't occur with aldehydes or ketones, so it will not work with those. To detect whether the reaction has occurred, the observation is a sweet-smelling liquid. Please note there will be acid catalyst left over at the end of the reaction, so you can't use pH or whether it reacts with carbonate as a way to tell whether or not there's any ethanoic acid left. Finally, the reason why the mixture is poured into the sodium hydrogen carbonate solution is that will remove any excess acid, be that ethanoic acid or the acid catalyst. Question B is a very similar reaction. It just wants to know which substances will react with toluenes. So toluenes is what we use to identify aldehydes. This time it is just aldehydes that will react, so no ketones, no alcohols. The only one that is an aldehyde is T, so the answer is T. The observation that you would see for that is silver mirror. For question E, you have to look at your datasheet and compare the functional groups on the isomers. R and S are both alcohols, whereas T is an aldehyde. This means that R and S will have a peak at somewhere in the range of 3,230 to 3,550 due to the OH alcohol group. T will not have a peak there, but it will have a peak at 1,680 to 1,750 due to the carbonyl, due to the C double bond O. So the question is, how do you tell R and S apart? Remember, all molecules have a completely unique fingerprint region below 1500. Fingerprint regions are useful because you can compare to a database of known substances and see if you have a match. Question F wants you to state why mass spectrometry using electrospray ionization is not a suitable method to distinguish between the isomers. This is because all the isomers have the same number of each atom, and therefore they have exactly the same MR. Something that's interesting to note in the question is that they specified using electrospray ionization. If you use electron impact ionization, you'd end up with a bunch of fragments. The fragmentation that occurs would actually be different in the different molecules, so you can use the fragmentation to tell them apart. Okay, so that brings us to the end of this video walkthrough of the carboxylic acid and esters practice test. If you have any questions, please leave a comment down below, and if you found the video useful, please leave a like.